Okay, here we're in R on a Ubuntu machine, and we're going to do this, calculate sample size in the multiple linear regression setting, and we're going to check hypothesis for the coefficient determination, or equivalently the multiple correlation coefficient. There's a package called Power, or PWR, that will load that has this test built in. We'll also do it from first principles. So as we go down, we need I want to create a plot. So we want alpha to be 0.05. We're going to have two predictors. We want the coefficient of determination 0.25, and F2 is the Cohen effect size. Cohen 1988, I think. Anyway, it's r squared divided by 1 minus r squared. So let's load that. Now, to create data, I want to go from, say, 0 to 12, a sequence, step size of 0.01. Here we're going to use a sample size of 20 to illustrate the null and what happens to our test statistic under the null and the alternative hypothesis. So there's our distribution under the null. This was a central F distribution. So to find the rejection region, we need to find the 5% in the tail, which is this. Then we need to calculate the distribution under the alternative, and we need the lambda, which is that's the non-centrality parameter. And then we create the distribution, and we need a shade above the rejection region, which then this is called power. It's the probability that you reject when you really should reject. And notice that this is not over half the area under the curve, so the power is not very high when we use a sample size of 20. So we'll need to increase it. And what it does is as I mentioned earlier, is it shifts this distribution to the right. And let's use the built-in, well, it's not the built-in, but a package called PWR. They have a power.f2.test, and we'll run that with two predictors, 0.25, significance level 0.05, and power 0.8. And we run that, and we get this. So what it does, it's actually solving for the the denominator degrees of freedom. Here's the numerator degrees of freedom, denominator, and it uses a function called uniroot. And anyway, so then we have to take the ceiling of that, and this next function, I save that to temp, and then I extract the numerator and denominator degrees of freedom, and then add 1. So we would need a sample size of 33 to make this power 0.8. It means that distribution is going to be shifted way to the right. Now, let's do another example. Here we have three predictors. R squared is 0.05. Effect size we're going to call F2. And then according to the package, power, PWR, we need 212 observations to have a power of 0.8. Now let's do this from first principles. And what you have to do is you have to start at a sample size, and that's lower than what you think the power would be. So I just add 2 to the number of predictors so we don't get any non-singularities. And then I guess what power will be. This is the rejection region, and then this is how you calculate power. So let's run that, and we get initial estimate of a power 0.05, which is too small. So we have to put it in this loop, and it just increments 1, checks power, and keeps going until we get over a power of 0.8. And so let's run that, and we need 212 observations, the same as what the package derived. I call this from first principles because it literally just, if that n wasn't large enough, it increments it by 1. It keeps going. Well, that is all I have for today. Hope you enjoyed it. I'm going to post the code in the comments so you'll see it. And if you look over here, I have more to this program which I'm not showing you, and it's pretty exciting. It's I just submitted a paper to the American Statistician that deals with this topic. It's a pretty creative way to find sample size in this setting. I'm not going to tell you more. In a couple weeks, I'll post a video describing that. But until then, that's what I have. Hope you enjoyed it. Please like the video. Please subscribe so you don't miss the next one. Thank you.